Welcome back to Hansen Theory. So far, you have learned molecular forces, Hansen space, Ra distance, red number, polymer behavior, solvent blend design, pigment-resin interactions, cross-linking and curing interactions, predictive troubleshooting, multi-component formulation optimization, and environmental effects on solubility and curing. Now, we move into modern coating technologies, waterborne and high solids coating systems. These systems are increasingly important due to environmental regulations, safety concerns, and sustainability goals. Hansen Theory allows you to design and optimize these formulations with predictive control, avoiding common pitfalls. Let's start with waterborne coatings. Waterborne systems replace volatile organic solvents with water. This reduces VOC emissions, but introduces complex molecular challenges. Water interacts strongly via hydrogen bonding and polarity. Polymers, pigments, and additives must be compatible not only with each other but also with water as the dispersing medium. In Hansen space, water has extreme polarity and hydrogen bonding values. Adding a polymer or pigment to water requires careful consideration of red. A polymer that is soluble in organic solvents may have red 1 in water, indicating poor compatibility. Co-solvents and surfactants are often required to reduce effective Ra and bring the system inside the solubility sphere. Now, co-solvent strategy. Waterborne formulations almost always contain minor amounts of organic co-solvents. These co-solvents improve polymer solubility, aid pigment wetting, modify drying rates, reduce red between water and hydrophobic polymer domains. Choosing the correct co-solvent type and fraction is a Hansen Theory calculation problem, not trial and error. Engineers calculate weighted contributions of water and co-solvents to determine the effective coordinates in Hansen space. Next, emulsion and dispersion stability. Waterborne coatings rely on either polymer emulsions or pigment dispersions. Hansen Theory helps predict emulsion droplet stability, pigment flocculation risk, surfactant effectiveness, polymer-polymer interactions in dispersed form. For example, a polymer emulsion may aggregate if Ra with water is too large or if red 1. Dispersants and surfactants reduce Ra distance by modifying surface interactions, stabilizing the system. Now, let's consider film formation in waterborne systems. Film formation is a dynamic process. Water evaporates. Polymer particles coalesce. Pigments settle or align. Reactive groups interact for cross-linking. Hansen Theory allows engineers to map red evolution over time during drying. This predicts potential defects such as cracking or coalescence failure, pigment floating or settling, incomplete curing. Next, high solids coating systems. High solids formulations reduce VOC content by increasing polymer fraction and reducing solvent. Challenges include high viscosity, reduced molecular mobility, difficulty in pigment wetting, cross-linking limitations due to diffusion constraints. Hansen Theory provides predictive control. Solvent selection or co-solvents maintain red 1, enabling polymer and pigment compatibility. Additive selection and ratio optimization ensure wetting, dispersion, and curing despite reduced solvent volume. Multipolymer and multipigment interactions are balanced using weighted coordinates in Hansen space. Now, polymer chain mobility in high solid systems. High polymer loading increases viscosity and reduces chain mobility. This can hinder curing and film formation. By mapping effective red for polymer-polymer and polymer curing agent interactions, engineers predict whether cross-linking will proceed efficiently. Co-solvents or reactive diluents are selected to optimize mobility without compromising environmental compliance. Next, pigment dispersion challenges. High solids coatings often contain high pigment volume concentrations, PVC. Pigments interact more strongly with each other and with polymers, increasing the risk of flocculation. Hansen Theory predicts these interactions. Surface energy mismatch and hydrogen bonding can increase Ra distance. Additives reduce red by stabilizing surfaces. Optimized solvent or co-solvent fractions prevent sedimentation or floating. Now, cross-linking in waterborne and high solid systems. Cross-linking requires reactive groups to come into proximity. In waterborne systems, water may hinder some reactions. In high-solid systems, limited mobility may slow reactions. Hansen theory predicts red changes as solvent evaporates or polymer chains move, enabling optimized curing schedules. Next, environmental and processing considerations. Waterborne coatings are sensitive to humidity and temperature. High-solids coatings are sensitive to shear and application method. Minority-thinking engineers simulate these effects in Hansen space. Predict red shifts during drying and curing. Adjust solvent/co-solvent ratios. Optimize additive selection. Ensure stability across environmental conditions. Now, sustainability and performance integration. Modern coatings must meet regulatory requirements without sacrificing performance. Waterborne and high-solid systems reduce VOCs, but challenge engineers to maintain gloss, opacity, adhesion, and hardness. By integrating Hansen theory, engineers design formulations that satisfy environmental, regulatory, and performance goals simultaneously. Finally, minority-thinking engineers approach these systems systematically. Map all components, including water, polymers, pigments, co-solvents, and additives in Hansen space. Calculate weighted RA distances and red numbers. Adjust formulation components iteratively to maintain red 1 for all critical interactions. Simulate environmental and processing variations to ensure robustness. Optimize performance metrics such as film formation, curing, viscosity, pigment dispersion, and mechanical properties. This is how waterborne and high-solids coating systems are designed for predictable, high-performance, environmentally compliant coatings. In the next episode, we will explore specialty additives and their molecular impact, showing how dispersants, surfactants, rheology modifiers, and other functional additives alter RA distances and red values to enhance coating performance. If you want to engineer modern, sustainable, high-performance coatings with precision, continue with this series. This is Hansen theory.